a balanced binary search tree. What is its runtime? Okay, and we have is it sums all the values of all the nodes in a balanced binary tree. And remember, we did the binary tree on page sorry, I'm also using the physical textbook for the background noises if it's irritating. Sorry. We did a binary search tree in page 44 of the Cracking the Coding interview. What is its runtime? Okay, so this is the code right here. In sum, you insert the node, and if the node is null, it returns 0. Else, it's a recursive function of the left node, the value, and then the right node. Okay, it says because it's a binary search tree doesn't mean it has log in it, but it has a relation to log. And we can look at it both ways. Okay, the first way, which is quite simple, is the way that the fact that it touches each and every node once. So it touches every node on the binary tree once. Hence, if we increase it to n, it is also going to be on. So I'm going to say first it is going to be on, and that's the answer. But in terms of looking at it in a bigger picture, it just touches each node. It's not searching, it just touches each node once on the binary search tree. So it will be on. If we add more elements, the runtime is going to increase proportionally. Okay, and the second way uses what we learned on page recursive runtimes on page 44. So let's just say it's based on page 44, the recursive runtimes, and she gave us a formula which is O2 to the depth. All right. Sorry. Apologies. She gave us, it was big O of the branches, which is normally 2, to the power of the depth of the recursion. Okay. Now, we know that it's a binary tree, so it has 2 branches. Okay, binary in this example, so it has 2 branches. Therefore, we have O2 depth. Okay, and then we have to work out the depth. Remember, on page 44, with the heading log n runtimes, we had an example of a binary search, and the binary search goes from n elements, which were about 16. N was 16, and then it searched less than 9. It went and it searched, it was an element that was less than 9, which comes up to, this gives us how much? It was half of that, which was 8. So here we had 8 elements, and it went lower again, and it went to 4, and it went to 2, and it ended with 1. Right, and this is comparative to the total n, which is given. This 8 is half. Okay, let's use a different color so it's not confusing. So let me just repeat that. This 8, which is after the first binary search, we had elements, and just on page 44, under the heading log n runtimes, we had to search for I think 9. We had to search for what did we look for? Okay, we have just, that's how binary search works. It goes and then there's a half, and we compare, is the number we're looking for above or below, because it's already sorted. And if it's below the half, we only take from less than the midpoint, and so on and so on and so forth. The relationship from 16 to 8 is dividing it by 2, right? Or you could just say 8 is 8 times, this is 8 times 2. 16, it's 16. 16 divided by 2. And then 8 to 4, I'm dividing it by 2. And then this again, we're dividing it by 2 or half. And then this and this divide by 2. But what happens if I throw a curveball and we don't know what the initial n is? As we're approaching n, we don't know what n is. N is not given as 16. N is some arbitrarily big number, right? So now it's easier for us to work from 1 going on to the n that's unknown, right? So that would be 1, that would be something like 1. So we're going to be multiplying it until we get to n. So it'd be 1 times 2, 2 times 2, 4 times 2, 8 times 2, so on and so forth, until we get n, which we're not really given, right? So now the question is, how many times must I multiply 2 to get n? And that can be encapsulated with the formula n is equal to 2x. We don't know what x is, right? Okay, so we then have to find what x is. We have the formula x, we have logs, which just means I find x, and that's log, and the base becomes 2, and that becomes n, right? So that's the logs. And we can do several examples. 2 to the 3 equals to 8. That can be written as well as making the exponent the subject, which is egg log 2, right? To the 8, that's the same thing. Or say 5 to the 2 is 25. You can write 2 as the subject, it's log 5. You can confirm this, 25. Okay, these are just examples. Sorry, I have to go in depth because this section really confused me. Now we know that to get the levels, this is now for n, right? So therefore the big O of binary tree is log n. This 2 is implicit in computer science, meaning if I write it like this, we already know there's a 2 there. Not really the same with general mathematics, but that's for another subject. So if I just write it like that, that is still correct. Now going back to the actual example 9, how does this relate to that? Remember we had this over here, we had this formula, and we're trying to find the depth going to n, right? It is therefore going to be O2, the depth is the log, right? Log n. That describes how deep from n that we will go given a certain input. That's how deep our branches are going to be. This is just trying to use the formula that she gave us on page 44. Okay, now the question is, how do we show that this is actually equal to O of n, that we know that this is the runtime of, just by reading the code, but using this formula that she gave us of branches to the power of the depth, right? So we will therefore say make this, because we will just make this entire formula. Well, you need to kind of know how logs work, and I think I gave you a nice example here. Logs work like there. We're trying to make the exponent the subject to find it, because most of the time we don't know. Say, for example, 2 is equal to 8, right? Now we want to know what x is. So x is equal to log. You take the base and you put it here, and you take 8 and you put it here. So reading this, you would read it as 2 raised to something, which is x, is equal to 8. So if you read this over here, and we know that the answer is 3. Same thing, you have 3 raised to the is equal to 9. We want to know what that x is, so we need to use logs. So we make x, the subject, is equal to log 3 to the 9. And how do we read this log? It says 3 raised to something, which is x, gives me 9. And if you use your calculator, you'll get the answer, and the answer is 2. Same thing with this, right? So we're saying this O2 log n is going to equal to p. This is just, okay, let me just remove the O, sorry about that. This is just sorry, I just wanted to come closer, but 2 log n. This is to just make it neater. Okay, so now we are attempting what we did previously. We want to make log n. We're trying to make this here the subject. We're going to therefore go log n, which is 2, which we said is implicit. You don't have to write it because computer science. We're trying to make this the subject, equal, okay, equal to log 2, the base becomes the base. You can actually write that as well, and the answer, which is p. I hope you understood. Just like this, and just like this, same thing. We're trying to make log n, the exponent, the subject of the formula. Okay, now we have this. Now we can drop the logs, and what do we get? N equals p. Wow, what just happened, right? This is also equal to n, this n. Therefore, right, remember we said p is equal to 2 log n, right? Now let's substitute this p for this over here. We say, sorry about that, we say n is equal to this value of p, which we said over here. Make a nice box over there, equals to 2 log n, meaning this n and this n are exactly the same thing. And we initially had that it is O2 log n. It's the same as saying O n. We've proved that. So you could move that over here. I think it makes more sense here, right? We said it's the big O using the formula of